Okay, welcome to our intro to trig and the circular functions. As we had talked about in class the other day, coming out of a geometry class where you may have studied the sine, the cosine, and the tangent operations on your calculator, we talked about how those three ratios are essentially just comparisons between sides of right triangles. For example, the sine of an angle compares the opposite side. So if we're talking about this angle here, alpha, its opposite side is y, and its hypotenuse is h. So we could write the expression that the sine of angle alpha is y divided by h, which just gives us a sense of how long is this side compared to the length of that side. Obviously, in a right triangle, this leg is going to be shorter than that, so when your numerator is smaller than your denominator, you're going to get a value that's less than 1. So a sine of an angle will be a value that's going to be less than 1, and we'll talk about expanding that a little bit more later on, but that's kind of a fundamental idea. And similarly, we have definitions for the cosine, which compares the adjacent side of the hypotenuse. So far we have two comparisons, the opposite compared to the hypotenuse and the adjacent compared to the hypotenuse. And then lastly, the tangent compares the two sides that have not yet been compared to each other, the opposite and the adjacent. Having said that, there's essentially just those three comparisons that can be made. However, if you wanted to consider comparing y to h as being something different than comparing h to y, then you could say, well, if we're talking about the reciprocal relationship, the cosecant of an angle compares the hypotenuse to the opposite as opposed to the sine of the angle, which compares the opposite to the hypotenuse. Not a whole lot of new information here, but you could write the statement that the cosecant of an angle, which is abbreviated CSC of alpha, would be the hypotenuse divided by the opposite. Similarly, the reciprocal of cosine is the secant of an angle. And lastly, the reciprocal of tangent is the cotangent, which compares the adjacent to the opposite as opposed to the opposite to the adjacent. Should be noted that notice the sine and the cosecant are reciprocals of one another, and the cosine and the secant are reciprocals of one another. So I will often say the cos don't go together, meaning it's a common mistake for people to think the reciprocal of cosine is cosecant, but it's not. The reciprocal of cosine is secant. Anyway, having said that, we can look at this picture over here to the right, which is a right triangle that has angles of 30, acute angle of 30 and 90 degrees, and I've labeled side lengths of 4 times the square root of 3, and 8, which are actually scale measurements. They're not so much scale measurements, but accurate measurements that could exist in a triangle with 30, 60, and 90 degree angles. And it's asking us for the sine of 60 degrees. So all we have to do is remember our SOHCAHTOA and how to spell it, and think of 60 degrees. And its opposite side would be 4 root 3. So the sine of 60 degrees is the opposite side, which is 4 root 3, over the hypotenuse, which is 8. And then reduce that and realize that 4 divided by 8 is 1 over 2, so we would get root 3 divided by 2 after we reduce that to 1/2. So the sine of 60 is root 3 over 2. And that's something that you could certainly go check on your calculator. As long as your calculator is in degree mode, you could punch in sine of 60, and it's not going to spit out root 3 over 2, but it's going to give you a decimal approximation of about 0.866. Then when you go to your calculator and put in the square root of 3 divided by 2, you'll find that exact same decimal approximation. Now, let's take a look and see if we can do part B here and look at the cosine of 30 degrees. So here's 30 degrees. Cosine, of course, is the adjacent over the hypotenuse. So we go to 30, look at its adjacent side, and we say the cosine of 30, the adjacent is 4 root 3, and the hypotenuse is 8, and we get exactly the same ratio, root 3 over 2. And we wonder, since we just got that for our first answer about the sine of 60, whether that's a coincidence. And chances are, since it's showing up on this note sheet, it's probably not. So I'm just going to put a big fat no there, and we'll see about what must be happening here. So while those are two, particular angles, 30 and 60, which occur together in this right triangle that I've drawn here, let's consider this original triangle that I put up here with its angle alpha and beta. These two angles Because this third angle here is a 90, we know that these two angles must also equal 90 because the total measure of the interior angles is 180. So for example, that means if I have a 90 down here and I have a 20 up here, this angle up here has to be 70 degrees because these two together must add up to be 90 to make 180 in the whole triangle. So if you take a look at these two angles, they must be complementary. And if you think about it for a minute, complementary angles add up to 90, and of course these two will add up to 90 because this one's 90, and you get 90 from those two and 90 from this one, and you're going to get the 180 that you need. So if we take that situation where we have a 20-degree angle here and a 70-degree angle here, and I don't know what this side length is or what this side length is or what this side length is, but I can tell you that the sine of 20 degrees would be the opposite, which is y, over the hypotenuse, which is h. But think about the cosine of 70 degrees. So for 70 degrees, its adjacent side is y, and its hypotenuse is h, and we get exactly the same ratio. So provided that these two angles are complementary, 20 and 70, 10 and 80, 40 and 50, 60 and 30, 85 and 5, any two angles that add up to be 90 degrees, the sine of one angle will be equal to the cosine of that angle's complement. Again, the sine of an angle is equal to the cosine of its complement. So pick an angle, I don't know, 15 degrees, the sine of 15 degrees. One thing I can be very sure of is it's exactly the same as the cosine of the complement to 15 degrees, which is 75 degrees. These two guys add up to 90. So the sine of 15 equals the cosine of 75. If you just think about it geometrically as far as what's happening, a 15-degree angle is a pretty small angle. So if you had a 15-degree angle here, this is going to be a 75-degree angle here. The cosine of 15 is measuring the relationship between this side length here and this side length here. You can see that this horizontal piece is almost as long as that hypotenuse is. So it makes sense that the cosine of 15 would be a ratio that's pretty close to 1. It's not going to be 1 because this side is shorter than that hypotenuse, but it's going to be fairly close to 1. I just went off to my calculator and said that and found out that the cosine of 15 is about 0.966, which essentially means that this side is about 96% as long as the hypotenuse is. But now think about it, that 75-degree angle that's up here in that corner, the opposite side of that is going to be measuring this compared to that. So it's going to be exactly that same value. So the cosine of 15 would equal the sine of 75. So there's a little idea that we can say is maybe our first little exploration into the patterns that might exist between these ratios, sine, cosine, and tangent. Will be 2. So continuing in that mode, now that we recognize that we have this generalization that we have right up here, the sine and the cosine are referred to each other as co-functions because of this relationship between those complementary angles, and that's literally where cosine comes from. It has to do with the sine of the complement. So that's kind of a cool little vocab trick that you can store in the back of your brain and remember forever and ever. So example 2 asks us that given that the sine of 20 is 0.342, find out what the cosine of 70 is. And if you just remember that 20 and 70 are complementary, you can say without doing any thought that the cosine of 70 is going to be 0.342. But to kind of bring this together, think about what we're saying here, that if we drew a 20-degree angle, again, that's probably a little bit more than 20 degrees, but certainly this side would be, that angle up there would be 70 degrees. And talking about the sine of 20 is 0.342. Well, if you think of 0.342 as 342 1,000ths, saying that the sine of 20 degrees equals 0.342 means that this side would be 342 if this side were to be 1,000. So you can get this picture that the opposite compared to the hypotenuse is 342 over 1,000. But most certainly from that same picture, you can see that the cosine of 70? Its adjacent side is the 342, and its hypotenuse is the 1,000. So the cosine of 70 would be exactly the same. Now, as I talked a lot in class, is that as we start to move further and further into our study of trig, we're going to start to work more and more regularly with radian measures. So here we've got pi over 3 radians, the secant of pi over 3, and it's asking us about the cosecant of pi over 6. So the first thing we need to do is remember that pi over 3, when we convert that to degrees, if you need to at this point, would be the same as 180 over pi. We're going to multiply those two together. And realize that pi over 3 radians, those pi's cancel out, and you get 180 over 3, which is 60 degrees. So to say the secant of 60 degrees, which is pi over 3, they're saying that that's equal to 2. And remember, you might not remember this yet, but you certainly will soon, that if we have a 60-degree angle, its cosine and its secant are reciprocals of one another. So saying that the secant of 60 is 2 means it's like 2 over 1. That's equivalent to saying its cosine of 60 is 1 over 2. In other words, the ratio of the adjacent to the hypotenuse is 1 over 2 is the same as comparing the hypotenuse to the adjacent being 2 over 1. So that means that we are talking about the adjacent side being 1 and the hypotenuse being 2. So if this guy is 60, that means that this angle's 30, and sure enough, to be asked about the cosecant of pi over 6, doing the same kind of work, pi over 6, when we multiply that by 180 over pi, we get 30 degrees. And so this angle here is our pi over 6. So if I were to redraw this in radian measure, this guy would be pi over 3, and this guy would be pi over 6, where we have a 1 here and a 2 here. And sure enough, the cosecant of pi over 6, which is what we're being asked about, that's the reciprocal of the sine. Sine of pi over 6 is the opposite over hypotenuse. So, of course, the cosecant of pi over 6 would be the hypotenuse over the opposite. So those two things are equivalent, and we can say that the cosecant of pi over 6 is the same as the sine. I'm sorry, is the same as the secant of pi over 3. And since this was 2. Okay, moving on a little bit more. After we get that relationship between sine and cosine and their cofunction truths that they have with them, we could now consider maybe one of the most important things, other than remembering SOHCAHTOA for all of our study of trig, and that's brushing the rust off of our old special triangles that we studied in geometry, and the special triangles being the ones that have angle measures of 30, 60, and 90 degrees, or 45, 45, and 90 degrees. I'm going to refer to them as the 30, 60, 90, the 45, 45, 90. Since we're talking about radian measure, though, we should probably go ahead and realize that pi over 6 is the same as 30, and pi over 3 is the same as 60, and pi over 2 is the same as 90. Lastly, over here in this guy, 45 degrees there is pi over 4. And if this angle's 45, then that angle's 45, which of course is also pi over 4. So it's really, really, really important to have these two triangles, this one and this one, kind of burned into your brain, understanding how the side length ratios play out, that the side length of 1 is the shortest side over here that's across from the smallest angle, 30 degrees or pi over 6. 60 degrees is like the medium angle, it's the middle one. With its radian measure of pi over 3, has root 3 across from it, which, for what it's worth, is about 1.7-ish. So it makes sense that this 1.7 is between 1 and 2, and 60 degrees is between 30 and 90. The longest side, of course, is across from the biggest angle. 90 degrees has 2 across from it. Over here, because these angles are equal, pi over 4 and 45 degrees, their opposite sides are equal. 1 is equal to 1, and then our hypotenuse is root 2. And again, root 2 for a numeric value, an approximate decimal is about 1.414. It's always good to have a rough idea of those in the back of your brain to sometimes be able to check and make sure if your answer makes sense or not. But you will need to have these two triangles memorized so that you can close your eyes and picture them and draw their side lengths and their angles at any given time throughout the rest of your math career. So once we have something like that burned into our brain, it should be really easy to come up with, for example, the sine of pi over 3. You say, okay, pi over 3 exists in this triangle. You think about its opposite side being root 3, and its hypotenuse being 2. And from this point on, you know that the sine of pi over 3 is root 3 over 2. It's never going to change. You can always bank on that. If you were asked about the tangent of pi over 4, you know you're shifting into this triangle over here, and tangent is opposite over adjacent, which is 1 over 1, which of course is 1. So if you have those two pictures burned into your brain, there's a whole lot of questions you now know the answer to as far as sines, cosines, and tangents, cosecant, secants, and cotangents for any angle, whether it's pi over 3, pi over 6, pi over 4, and we'll even talk about pi over 2 in our next section. Lastly, we have this example here that asks us about could we figure out what angle it is so that its tangent is root 3 over 3. Now, we should be able to do this without a calculator, so already we're a little suspicious because although I see a root 3 here, I don't see a regular 3 around in my triangles anywhere. That's a little suspicious. But if I remember that this is the same as root 3 over 3, where we write 3 as root 3 times root 3. So think about this just for a second. Root 3 times root 3 is 3, so the denominators are the same, and root 3 is the same as root 3, so the numerators are the same. But now you see this fraction, you say, hey, wait a minute, I can cancel out that root 3 with that root 3, and we get 1 over root 3. Now, if I know that the tangent of some angle is 1 over root 3, I can start to picture that angle. So that angle, let's think of it, would has an opposite side of 1 and an adjacent side of root 3. So here's an angle that has an opposite side of 1. That pi over 6 has an opposite side of 1 and an adjacent side of root 3. So that angle must be pi over 6. Now, the fact that they said the angle was acute means we know it fits inside of one of these right triangles there. So it had to be done without a calculator. The answer had to be either 30 or pi over 6, 60 or pi over 3, or pi over 4. Those three angles are going to provide the basis for much of what we do without a calculator in this class. So if you had to guess an angle that they're looking for, chances are it's going to be pi over 6, pi over 3, or pi over 4. We just had to make sure we had the right one that had the right sides in the right orientation. And lastly, we can move through example 5 here. That's telling us about an angle that is an acute angle, and we know its sine is 5/6. So if we could think about drawing a right triangle and labeling an angle as theta, right angle there. And we know just this much, that the sine of that angle is 5/6. So that means necessarily that its opposite side must be 5, and its hypotenuse must be 6. So to say that the sine of theta equals 5 over 6, we have a relationship between the opposite and the hypotenuse. Now, we don't, I should clarify that. We don't know that this side is 5 and this side is 6. For all we know, this side could be, it could be 500 over 600, but that ratio has to be the same as 5 to 6. So we're just going to work in its simplified form. But the question is asking about coming up with the other 5 trig ratios. Well, there's one I can think of that we can get for free, and that's the cosecant of that angle, which is simply the reciprocal of the sine. So that has to be 6/5. Well, we did that without any math. But to come up with the cosine and the tangent, we have to do just a little bit of math, because both the cosine and the tangent involve this adjacent side. Tangent is opposite over adjacent, and cosine is adjacent over hypotenuse. So we're going to need to figure out what this side is. Well, we can do that easy enough, just realizing that if we call this guy x, that we have a right triangle here. So good old friend Pythagoras says that x squared plus 5 squared has to equal 6 squared. So we come off to the side, x squared plus 5 squared equals 6 squared. So if you do the math, you're going to get x squared equals 11. 36 minus 25. So x must be plus or minus root 11. But because we're talking about a side length here, we're going to say that x must be the positive version of root 11. So I'll put a root 11 here. And now we can answer any question they want. The cosine would be the adjacent, which is root 11, over the hypotenuse, which is 6. And that means the secant is its reciprocal, which is 6 over root 11, which would be the same as 6 root 11 over 11 if we fixed the denominator, rationalized it. The tangent of that angle would be the opposite, which is 5, over the adjacent, which is root 11, which we could change to 5 root 11 over 11. And of course the cotangent, which is the reciprocal, would just be root 11 over 5. And you can see I just reciprocated this version here to flip it to get this version here, knowing that we would have a radical in the numerator there and that wouldn't be an issue. So there you go, nice little intro into the world of trig ratios and how they work, how they're related to each other. Probably the single most important thing you got coming out of this section, though, is being able to draw these two special triangles, the 45-45-90 with its radian measures of pi over 4, and pi over 2, and the 30-60-90 with its angles 30 degrees is pi over 6, 60 degrees is pi over 3, 90 degrees is pi over 2, and its side lengths of 1, root 3, and 2. Being able to draw those from memory is critically important. All right, thanks a lot.